Hello sir, my name is Mazlan Mustafa and now I will talk about beams. As you can see at the figure above, the permanent load is GK is 1.0 kN meter square excluding self weight. Variable load is QK that equal to 0.1 kN meter square. And then from the data that was given, we design the beam. 1 A2B. So the formula is weight equal to 1.35 GK plus 1.5 QK. So we calculate and then we get the design beam AB is equal to 0.75 kN meter. And then we calculate the same thing at the design beam 1A A2B, design beam 1A D to C, and design beam 1A to D. After that, we calculate the reaction at the A to B, which is we get reaction B that is 3.75 kN meter and reaction A 3.75 kN meter. And then we sketch a free body diagram. As you can see, that is our free body diagram. After that, we sketch again a free body diagram from A to D, which is we get the reaction at D is 2.974 kN and reaction at A is 4.81 kN meter. And then we select section and determine geometry, which is we follow the table properties. We follow the table properties that says of the beam, and then we classify cross section, and then we get 0.992. Then the outstand flange is 5.54, which is smaller than 8.28. That means flange is class 1. And then we calculate the web, which is the web is 49.3, which is smaller than 66.24. That means the web is class 1. Therefore 610 times 229 times 113 UB section is class 1. After that, we calculate the bending resistance of cross section, which is we get the value of MCYRD is 902 kN per meter, which is larger than 18.75 kN meter. That means the cross section resistance in bending is okay. After that, we calculate the MCR and WPI-FY, and we get the MCR is 1352 kN per meter. After that, we calculate the non-dimension slenderness. That we get the H per B is 2.86. After that, we determine the imperfection factor for buckling BA, that is 0.34. Then we calculate the buckling reduction factor X, and then we get the value LT is 0.711. And then we design buckling resistance MBRD, which is we get 641 and 32 kN per meter. And then we check that segment 1A to D is okay.
Hello Sir Rifat, my name is Ainul Farhana binti Salamin with the matrix number 07DK820F1035. Today we will be present about column. A column or point of support in design and underlying designing is a primary component that communicates through pressure the heaviness of the construction above to other underlying components underneath. At the end of the day, a section is a pressure member. The term segment applies particularly to a huge round hulk with a capital and a base of platform which is made of stone or having all the earmarks of being so. A little wooden or metal hulk is normally called a post, and support with a rectangular or other non-round segment are typically called piers. with the end goal of wind or seismic thermal designing. Segment might be intended to oppose parallel forces. Other pressure individuals are frequently named segment due to the comparative pressure condition. Segments are every now and again used to help shaft or curve on which the upper pieces of wall or roof rest. In design, sections allows to such an underlying component likewise has specific corresponding and embellishing features. A second could likewise be embellishing component not required for underlying purposes. Nemesis segments are locked in other words, structure part of a wall. A long succession of segments joined by an entablature is known as a colonnade. So this is the analysis. The total compression load equals to 9.17 kN. The nominal level equals to 0.68 and 12.177. The distribute level 1 equals to 0.34. And then the design bending moment due to eccentricities. So the nominal moment at level 1 equals to 387 kNm 2 and 12.03 kNm. So the distribute level 1 equals to 193.5 kNm and 6.02 kNm. The design section properties equals to, as you can see, this equals to 10.2 mm, and then material properties is steel grade, and the partial factors for resistance equals to 1.0. This is the flange and web. Therefore, section is class 1, minimum buckling resistance. This is the column slenderness, buckling length L, and then this is the column imperfection. And then this is the slenderness of column. In this design example, the reduction factor XLT due to LTB is calculated based on the exact approach clause 6.3.2.3. And then this is the column imperfection. And then this is the lateral torsional buckling resistance, the sectional resistance interaction equation. And lastly is the section size 203 times 203 times 52 UKC is satisfactory.
Good morning to Surek Futbong. My name is Nushafiran binti Kadapi with matrix number 07DK20F1048. So today I'm going to present about connections. The conventional method of connecting beams to column is to provide moment transfer via full penetration butt welds between the beam flange and column flange, strong axis connection or continuity plates with axis connection, and shear transfer via the beam web connection. The joint connecting beams and column in a reinforced concrete frame structure is an important part during the earthquake because the maximum values of shear force and bending moment occur simultaneously, and damage is easily resolved there under seismic load, and additional damage or even collapse of the structure may be caused after its failure. So this is the calculation of shear and torsion. A connection is subject to ultimate load of 6.K Newton. Check whether 24 mm bolt size in grade 4.6 is suitable. Eccentricity between point load to centroid of column is 300 mm. A connection is subject to ultimate load of 6.4 kN. So analysis of external force, details of holes and bolts. Bolt V equal to 24 mm, holes E1 equal to 50 mm, P1 equal to 100 mm, and DO equal to 26 mm direct shear. Fs in bolt A. Fs equal to 0.8 kN. Shear due to torsion Ft in bolt A is equal to 2.5 kN. So the answer is 35.6 kN. While for the design resistance against external force, try 24 mm bolt, hence D equal to 24 mm hole diameter, DO equal to 26 mm. Shear resistance of 1 bolt equal to 67.7 kN. Bearing resistance per plan, the answer is 67.78 kN. Therefore, 24 mm diameter of bolt of grade 4.6 is satisfactory for the connection. While for the shear and tension, using 24 mm bolt in grade 4.6 and steel in grade S355, the design resistance against external forces. So the answer is 0.01.0. The connection can support the load safely. So that's all from me. Thank you.
My name is Muhammad Shamil Mirul. My matrix number is 07DK80F1020. So I will present chapter 2, thrust. For analysis of thrust, the loads from the roof sheet transferred to the purlin are as follows. Permanent load of slope GK, aggregate steel roofing equals 0.15 km per square. For lightning and insulation equals 0.10 kN meter square. For the self-weight of purlin is 0.05 kilo Newton square. For the self-weight of truss 0.1 kilonewton meter square. For the variable loads on slope is Q equals 0.5 kilonewton meter square. Therefore, the net loads on slope GK equals 0.4 kilonewton meter square. For variable loads on slope is QK is 0.5 kilonewton meter square. The detail of thrust spacing between trusses is SC is 5 meter, while purlin is spacing 2 meter. For the factor head load is Q equal 1.5 GK plus 1 QK. So we get 1.29 km square. For the area of load transfer to any intermediate nodes, we get 10 meter square. For the point load at the nodes, we get 12.9 kilonewton. For shear force V, we get 25.8 kilonewton, and for F5, we get 25.8 kilonewton. And let's calculate of joint. For the joint A, we get FAH equal 25.80 kilonewton. Tension for the joint H, FHG equal 25.8 kN. Tension for the joint B, FBC equal 21.5 kilonewton pressure. For the joint G, FCG equal minus 38.70 kilonewton tension. For the compression member, we get 4, and tension member, we get 3. And roof trusses are end member connected with 2 bolts of 20 millimeter diameter. From analysis of truss, the maximum design of tension force in a truss member is NED equal 38.7 kN. The member consists of an equal angle is 200 times 150 times 12 and of steel grade S275 for the AG 4080 meters square, for IY 64.3 mm, IZ 26.7 mm, IU 66.3 mm, IY equal 21.4 mm, T 12 mm. For design of tension member, design strength Fy T 12 mm, seal grade is 275. So we get 40 mm is bigger than T. Therefore, Fy equals 275 n millimeter square. Fu is 430 m square. Diameter of both D equal 22 millimeter. For section with holes, design tension resistance and TRD should be taken as the smaller of. So the design plastic section of gross cross section, we get 1122 km. The design ultimate resistance of cross section at holes per fastener, therefore MTRD we get 1165.89 km. So we check 38.70 over 1165.89, so we get 0.03 is smaller than 1.0. Therefore, section 200 times 150 times 12L is suitable to carry the tension force. For design of compression member, design strength E equal 0.682. For the cross section clarification, H over T, so 200 over 12 equal 16.67 is bigger than 15E. For the B plus H over 2T, so 150 plus 200 over 2 minus 12, so we get 14.58 is bigger than 11.58. Therefore, section is class 3 and suitable for local buckling. The small radius of this garrison, IB 21.4 mm, will contribute to the largest slenderness. Hence, V minus B is the weakness axis. Note that the larger the slenderness, the weaker is the axis, but bulking system about the weakest axis. So the way the capacity of reduction factor is given as reduction factor X. So after the calculation, we get 3.35 kilonewton. For the expression of bulking curve to calculate the bulking system, so we get 123.52 kilonewton. So we check 32.25 over 123.42, we get 0.26 is smaller than 1.0. Therefore, section is suitable to carry the compression force. Thank you.